Hola Marcelo, ¿qué tal?
De Ciencias Nucleares. Ayer algunos de ustedes nos acompañaron. Gracias por estar aquí de nuevo. En esta ocasión tenemos a un invitado muy especial, es un amigo de hace muchísimos años, personal, pero además es un mentor, un muy importante mentor que yo tuve para comunicar antimateria también hace muchísimos años. Habla español, así que no digan groserías, porque sí las va a entender, aunque no se las va a entender. Entonces, les quiero presentar al profesor Michael Dozer. Les voy a leer un poco sobre su historia. Es un investigador físico del CERN, estudió estudios de física en el ETH-CERN, estudios de doctorado en la Universidad de Zúrich. Hizo su postdoc en el Keck en Japón y fue es el Deputy Department, ¿cómo se traduce? Es como el líder de los, o digamos el jefe de investigación, ¿sí?, del Departamento de Física del CERN de 2006 a 2008. Desde 1983 ha trabajado en antimateria usándola tanto como herramienta para estudiar la interacción fuerte en los experimentos Asteris y el Barrel Crystal, y ahora ha estado, que habían estado buscando estados no QQ barra, bueno, en español no sé cómo se dirían, pero en realidad, ¿perdón? Quark antiquark, exacto. Sí, estudios de quark antiquark y como hadrones de solamente gluones o hadrones híbridos. También lo ha estudiado como un objeto de estudio a la antimateria, la formación de antiátomos, la estudio de asimetrías entre materia y antimateria, y trabajos hacia la medición de la interacción gravitacional entre la materia y la antimateria. Es también el vocero del experimento AEgIS en el CERN. Además, da muchas charlas sobre antimateria y es editor de Physics Letters B y del Review of Particle Properties. Entonces, pues no me queda más que dar la bienvenida, gracias, y gracias al proyecto de Ale de la Puente, Esperando el Relámpago, porque de verdad los artistas logran muchas cosas que a veces del lado de la ciencia no podemos lograr, como traer a científicos de este grupo tan importante. Muchas gracias. Thank you, Michael.
Thank you. So thank you very much for the introduction. I will speak in English, although I could probably muddle through in Spanish, but it will be so much easier for you to understand what I say in English. So I will be talking about experiments on antimatter. In fact, the work that has been done in the last 10, 15 years at CERN, which is the only place in which these experiments can take place. It's the world's only source of antimatter. And I'll say a little bit about that. But mainly, I will talk about what kind of experiments. Why is this not working? Sorry. It was just slow. But what kind of measurements we're trying to do when we study antimatter? And there are three systems or three questions that are really being looked at. The first one is to look at the gravitational behavior of antimatter, to try to test the weak equivalence principle in another system than the one that one normally does by varying matter-matter interactions. So here one looks at matter-antimatter interactions. The second field of activity is precise spectroscopic comparisons between matter systems and antimatter systems. So the spectrum, the light spectrum of hydrogen and of antihydrogen, but there are other systems that I'll talk about afterwards as well. And this is a way to test the fundamental symmetry CPT. And then there are further measurements in antihydrogen-like systems, also neutral system, like antiprotonic helium, where an electron of the helium atom is replaced by an antiproton, or positronium, an electron-positron bound state, or even protonium, a proton-antiproton bound state, an atom of those two. So to start out with gravity, you know that gravity is a classical non-quantum theory, and it's described by general relativity. But if you try to transform this non-quantum theory into a quantum theory of gravity, in some of these quantum theory attempts, Einstein equivalence principle violations can appear. And I'd just like to give a toy model, which is wrong, so don't take this seriously, but it's to show you the kind of things that one might hope to be able to feel or to detect. If you look at a model where the tensor graviton, the spin 2 particle, is complemented by two further graviton-like particles, a gravivector with spin 1 and a graviscalar with spin 0, then in such a model you can have interactions which can violate the equivalence principle. And the reason for that is if you look at the potential that you normally get, where you have two masses interacting gravitationally via the spin 2 particle, then these gravivector and graviscalar interactions add two further components which have an intensity, a strength, and a range. So the intensity is A, the range is V. And because of the symmetry of the interaction, in the case of a scalar interaction, the charge of the particle is equal to the charge of the antiparticle. You have an attractive force. The sign between these two here is plus, just like the sign for the tensor interaction. But for the vector interaction, the charge of the particle is then opposite to the charge of the antiparticle, and depending on which kind of interactions you're getting, particle-particle or particle-antiparticle, you can end up with a repulsive or an attractive force. In other words, the sign of this component here can change depending on whether you have a matter-matter or matter-antimatter interaction. And if you're lucky, lucky in the sense of us as experimenters, then you can have cancellation effects if these two strengths and these two ranges are comparable. So that for matter-matter interactions, these two might just simply cancel away, whereas for matter-antimatter interactions, then one of these components comes out, and you might see a difference in gravitational interactions between matter and antimatter. The other area that one can look at is CPT. Now, CPT is a very fundamental symmetry. It's part of the standard model, and one can prove that CPT is a good symmetry in quantum field theories. But you can extend the standard model. And in fact, there's a group around Alan Kosteletsky that's been doing that for the last 20 years, writing down extensions to the standard model which lead to modified Dirac equations. So this is the standard Dirac equation, and if you go into this standard model extension, you get further components, further interactions in a way, that can either lead to CPT and Lorentz violation or simply to Lorentz violation alone. And you can get, in certain string theories, spontaneous symmetry breaking, Lorentz symmetry breaking. So this and that can lead to CPT violations, symmetry violations. And you can detect those in principle if you do a measurement over the course of a day, over the course of a year, as the laboratory system moves through a preferred frame, a preferred direction, which would then lead to variations in interactions. So experimentally, what you do is you try to measure the spectroscopy of hydrogen and of antihydrogen, and what one really wants to focus on are two transitions in the case of hydrogen. It's the transition from the ground state to the first excited state, the 1s-2s transition, which has to be a two-photon transition because of the same spin here and here. This excited state has a very long lifetime of about 100 milliseconds, which means that the uncertainty on the energy of this transition, the natural line width of this transition, is about 10 to the minus 15. And in fact, it has been measured by Ted Hensch and other workers in his group to a precision of somewhat better than 10 to the minus 14. The other transition that's very interesting to look at is the splitting of the ground state, the hyperfine splitting of the ground state, which has been measured to 1 part in 10 to the 12 by Ramsey. And in the case of antihydrogen, one would like to show that these two transitions are identical or perhaps different. If they were different, then that would be a sign of CPT violation. So the experiments looking at these kinds of systems are all placed at the antiproton decelerator at CERN, and the 6 experiments that are working there are either focusing on spectroscopy of antimatter-matter systems or of purely antimatter systems. That would be the ALPHA experiment, the ASAXA experiment, the ATRAP experiment, and to some extent the AEGIS experiment. Or looking at gravity, that's the GBAR experiment, the AEGIS experiment, the ALPHA experiment. Or looking at fundamental symmetries by comparing charged particles with charged antiparticles, and those are the BASE and ATRAP experiments. There are also some experiments looking at interactions with antimatter with biological systems, but I won't be talking about that at all. I'll really be concentrating on these experiments here. And to start out with, I'd like to start with ATRAP and BASE, who study the behavior or the properties of antiprotons and protons, or electrons and positrons, as precisely as they can. And in order to do that, they place the charged particles into a magnetic field, where one then gets a cyclotron frequency, a cyclotron orbit, whose frequency is given just by the strength of the field, of the magnetic field, and the charge to mass ratio. If you just have this, then of course the particles will just move in a circle. If you in addition add an electrical potential, a well like this, then charged particles will go back and forth but fly around in a magnetic field. And so if you look at the overall trajectory that these particles will follow, it's a complex trajectory between the axial motion defined by the axial electric field, the cyclotron motion, which is defined by the magnetic field, and the magnetron motion, which is given by the E cross B field. And if you look at the motion equations of these particles in that kind of environment, you can separate it into these 3 frequencies, into these 3 motions. A modified cyclotron motion, which has a frequency of the order of 100 megahertz in these experiments, the magnetron motion, which is of the order of 1 megahertz, and an axial motion, which is of the order of 10 kilohertz. And what you try to do is, by looking at the frequencies of the particles inside a magnetic and electric field, is to extract these 3 frequencies, from which one can then extract charge and mass. So this is a picture, then a sketch, a somewhat bigger sketch, of what one of these apparatuses look like. This is the BASE experiment, where one creates an axial electric field through a series of ring-shaped electrodes embedded in a strong magnetic field. And you can measure the effect of these particles by looking at a signal picked up on one of these electrodes as the particle comes close or moves away from it. So this would be the axial motion that gives you a slightly induced signal. If you split these electrodes like this in 2 or in 4, then as the particle goes around, it will also induce a current in the electrode segments as it gets closer or goes away from it. So by looking at the induced signals, you can measure the frequencies of the particles and then extract charge and mass. But you can do something more than that. You can also extract information on the magnetic moment. Because if you look carefully at the axial frequency, it will depend on whether the magnetic moment of the charged particle is parallel to the magnetic field or anti-parallel to the magnetic field. The energy levels are slightly different, and if you can measure in what state the particle is, then you can extract, through the difference in axial frequencies, the magnetic moment of the particle. And in order to measure the position, the spin orientation of the antiproton, both the A-trap and the base experiment, in fact mainly the base experiment, induce a spin flip by including a very strong magnetic field gradient in an axial direction, so that the interaction of the charged particle with this magnetic field gradient can allow you to flip the spin. And by doing that, they can measure which state the particle is in, the antiproton is in, and measure the axial frequency for the 2 orientations. And by doing that, they've measured the magnetic moment of the antiproton, the proton, to about 1 part in 10 to the 6 in 2013. Base improved on that measurement in 2017, so this is the best measurement in 2013. In 2017, base improved on that and is now at the level of 10 to the minus 9 by doing very, very precise measurements over very long periods of time of the frequencies. So this is a period of about a month and a half, and what they're trying to measure is the centroid, the position of the center of all these different values. So if you look at the evolution of the measurement of the magnetic moment as a function of time, this is in 1985, where the measurement, the precision with which the magnetic moment of the antiproton is known is about 1%. And then in the course of about 30 years, it's gone down to about 10 to the minus 9. And this experiment is on the way to getting another order of magnitude or 2. Note that there's no difference. This is exactly the same value as that of the proton. And if you look very carefully, you'll see that the error on the antiproton magnetic moment is now smaller than that of the proton. We know the magnetic moment better for antiparticles than for particles. There was another way to measure the magnetic moment. This was done before, but there's also the same system can be used to measure the charge and the mass of the antiproton. The system is an exotic atom, antiprotonic helium. So when injects antiproton into helium gas, through Auger effect, one of the electrons is kicked out and the antiproton is bound, and you end up with a system which has a helium nucleus, an electron, and an antiproton, which forms an atom with energy levels. So these are the energy levels of this atom with one very heavy electron. And these states here in red live for a very long time. They live for microseconds. But if you can induce a transition between one of these very long-lived states and a state in blue or in green, which has lifetimes of the order of nanoseconds, then you can measure the energy differences between these states. If you can measure the energy differences, you can compare the measurement with calculations, 3-body calculations, into which mass and charge of the antiproton flow. And by doing this very carefully over many, many years, the Aegis experiment has measured something like 20 different transitions, either in antiprotonic helium-4 or in antiprotonic helium-3, at the level of part per trillions. So the measurements are in red, and the theoretical, the measurements are in black, and the theoretical predictions are in red. These are QED calculations to 6th order. So the theorist that has spent his life calculating these transitions must be rather frustrated because everything agrees so well with the measurements. Again, there was hope to see a difference between matter and antimatter. What one finds, if one combines these measurements with the measurements of A-trap and base, which measure the charge to mass ratio, is that the mass difference and the charge difference between protons and antiprotons is less than about 1 part in 10 to the 10. So no sign of CPT violation at that level. Which means that we have to change systems to get something more precise, to be able to actually probe more deeply. And this means that we have to work with neutral systems. Charge systems will always be sensitive to external fields, magnetic fields, electric fields. The only system that the antimatter system that people have looked at up to now is antihydrogen. And one has to bear in mind that the number of particles we're working with is of the order of about 10 to the 6 antiprotons and about 10 to the 8 positrons, which you have to then combine to make atoms of antihydrogen, which is, in the best of all situations, going to give you a few 100,000 antihydrogen atoms to play with. And so you better come up with a very efficient way of making antihydrogen so that you can then study a handful of atoms. And this is a problem because if you rely on this formation mechanism to make antihydrogen, where an electron, or a positron in this case, is captured radiatively by an antiproton and the binding energy emitted in form of a photon, this process has an extremely low rate. And so you won't end up with very many antihydrogen atoms that you can study. This process has never been looked at. We actually haven't tried it because it has a very, very low predicted rate. Instead, the experiments currently taking place rely on two other processes: a three-body recombination where two positrons are close enough to each other and to an antiproton that the antiproton can form an atom with one of them, while the other one carries away the binding energy in form of kinetic energy. This three-body recombination and the other production process that is being worked on is resonant charge exchange, where the positron is brought in form of a positronium atom, and the binding energy is carried away by the electron of the positronium. So this process here is used by all the running experiments, Alpha, ATRAP, and Azaxa, and it really requires holding at the same time a cloud of positrons and a cloud of antiprotons and gently pouring the antiprotons into the positron cloud. The temperature of the resulting antihydrogen atoms is determined by the temperature of the positrons because it's a question of velocity matching. When the velocity of the antiproton and that of the positron is matched, then one can form antihydrogen. And because for a certain temperature, the velocity of the positrons is much higher than that of the antiprotons, the velocity will end up being high. This is a hot antihydrogen atoms of the order of 100 Kelvin. The rate for this production process is very high. One can get about a kilohertz production rate with the numbers I gave before, but only a tiny fraction of those are trappable. One can only trap about 10 to the minus 4 fraction of the formed atoms, but then if they are trapped, they have time to cascade down into the ground state. So this is a very good source of ground state antihydrogen inside an apparatus. The other method, resonant charge exchange, is being worked on by AEgIS and GBAR, and contrary to this method, has not yet been shown to work. We're still in the process of trying to get it to work. It has the advantage that the temperature is now defined by the temperature of the antiprotons, which should in principle be easier to cool down to lower temperatures, but the rate is very low. Compared to this process, there's a factor of about 10 to the 3 to 10 to the 4 reduction. On the other hand, the rate of those that can be trapped is good. And so at the end of the day, the number of trapped atoms in both cases should be comparable, but these atoms should be colder. So it's a very promising technique, but it hasn't yet been shown to work. Contrary to the three-body recombination, which works very well and has been used by the Alpha collaboration for about a decade now to form antihydrogen, but also to trap antihydrogen. In order to trap these antihydrogen atoms, one uses the fact that the ground state of antihydrogen has 4 energy levels, which can be split in a magnetic field gradient. The Zeeman splitting means that you have 2 levels that increase potential energy as they go into a magnetic field. So as the atom starts here and goes in here, it loses kinetic energy to gain potential energy, and 2 levels which lose potential energy and thus gain kinetic energy. These cannot be trapped, but these here can be trapped if the initial energy, the initial kinetic energy, is lower than the gain in potential energy, and this means for realistic traps a temperature of about less than 100 millikelvin. So atoms that are formed with a temperature below 100 millikelvin can be trapped. Atoms that are formed with a temperature higher than 100 millikelvin will not be trapped because they are not slowed down enough before they actually hit the ring electrodes with which the charged particles are being held. So you recognize again the same structure as before. You have these rings inside an embedded in a very strong axial magnetic field. But in addition, you can see these bars here that by running a current through them create a very strong gradient between the bars. And so you actually end up forming about a 1 Tesla gradient difference between the center of the trap and the wall of the trap. In 2010, the alpha collaboration got this apparatus to work and started forming antihydrogen atoms in it with the trap on, and then tried to prove that they had actually trapped antihydrogen atoms. And the way you can prove that you've trapped atoms is by forming the atoms, holding on to them, and then after a certain amount of time, releasing them. As you release them, they will touch the wall, and when antihydrogen atoms touch matter, they annihilate and produce pions. These pions then fly through a multi-layer silicon strip tracker. So you get tracks, and you get the vertices, and you can reconstruct the axial and the radial position of these vertices. So opening the trap happens at time equals 0. That's this direction here. And what is shown here is the z-axis of where annihilations were recorded after opening the trap. And each one of these colored dots is one annihilation. It's one signal, one vertex. And you can see this distribution. In gray is the distribution that they expected for antihydrogen atoms. And you can see they match very well, but that wasn't good enough. They wanted to really prove that this could not be due to any antiprotons that were trapped in their apparatus. And in order to show that, they applied an electric field gradient at time equals 0 once they opened their trap. So if you have any antiprotons that are still inside the apparatus and you apply a field, they will be pushed in one direction. And so they will end up annihilating early and at a different Z position than what you expect for antihydrogen. This is one electric field gradient, this is the other electric field gradient, what you would expect for these different applied electric fields while the dump is happening. And one can see that the annihilations absolutely don't match the signal you would get for antiprotons and match very well the signal you get for trapped antihydrogen. So with that, they had managed to trap antihydrogen atoms for the first time, and this then allowed them to continue studying these antihydrogen atoms. First by shining light into the apparatus. So the apparatus that they have is open on both ends, and one can shine a laser light into the apparatus. A laser light leading to excitation of antihydrogen, and when the excited atom falls back into the ground state, and possibly spin flips, loss of antihydrogen atoms. So if you're on resonance of the laser, then with the power that they have, they were expecting to see about 50% of their atoms disappear and 50% of their atoms still remaining trapped in the apparatus. And in fact, what they found is that 60% of their atoms survived being blasted with the 242 nanometer laser. And with that, they did the first measurement of the 1s-2s transition to 1 part in 10 to the 10. So remember, for matter, it's known to 1 part in 10 to the 15. This is the first measurement on antihydrogen, and immediately they get 10 to the minus 10 precision, which is very, very good. They also measured the charge of antihydrogen, which should be 0, and which they managed to show is less than 1 times 10 to the minus 9 times the charge of an electron. And they also managed to trap a number of antihydrogen atoms simultaneously. So this is a little while ago. And in the meantime, they have not been idle. They've done 2 further measurements, which are significant. First of all, they've measured the hyperfine splitting of antihydrogen. So what you're trying to do here is you've got trapped atoms in the apparatus. They're on these 2 possible states. And if you shine a microwave corresponding to this transition or a microwave corresponding to that transition, you will depopulate the number of atoms that are in here. So if you know how many atoms you have, you shine a microwave frequency at it, and then you count how many atoms are left. As you scan the microwave frequency, you should be able to see a drop in population. And at the same time, you can also count how many atoms are being lost while you're shining the microwaves in. The microwaves are not very powerful, so they shine them for about 10 seconds or 15 seconds. There's a lot of background during that time because there are cosmic rays going through the apparatus, but they were able to differentiate the two. And so what they show is that as you shine the microwave in as a function of the frequency, you see 2 lines. You see this line here, relative to 1.42 megahertz, and this line here. So these are the 2 transitions that you want to see. And this allowed them to measure the hyperfine splitting of antihydrogen to about 1 per mil, which is the first ever measurement of that as well. That was in 2017, so this is relatively new. And the most recent measurement that they've done is the measurement of the 1s-2s transition, but this time seriously. So this is a little bit tricky, and I'm going to have to explain it a little bit more in detail. What they do is they have these 2 states here, And they can now try to count how many atoms go up and come back down again from one of these or from the other state by trapping the atoms, using the microwave that I just talked about to depopulate one of the two states. Then one is left with a pure system of only, say, the 1sc or the 1sd line, then exciting that one, and then with the same photon that you use to excite them, photoionizing them. So you use two photons to excite them, and then a third photon to photoionize them, having applied a microwave beforehand to do a depopulation, a selective depopulation. And then once that is all done, they can then still probe what's left in here by again applying microwave light to depopulate and destroy the atoms that are in here. So they can fully measure all population states as they go along, as they detune the laser that they're using to go from this state to this state. And that allowed them then to do a measurement of the 1s-2s transition to 1 part in 10 to the 12. So another 2 orders of magnitude improvement to the measurement they had done 4 years earlier. And unfortunately, this is going to be pretty much the end of the road for now, because these atoms are still relatively hot. They're at a temperature of 100 millikelvin, which means that you have Doppler broadening, you have a Doppler shift of these atoms, and even worse, because these atoms are in a magnetic field, which is not 0 at the origin, but actually 1 Tesla, because that's what they need to hold the atoms. Otherwise, you get a spin mixing of these states and these states, and your trap empties very quickly. Unless they can remove the magnetic field and cool the antihydrogen atoms, they're going to be stuck more or less at this level for now. So this is state of the art. It will be improved, but what is required is cooling of antihydrogen atoms and lowering of the magnetic field, the trapping field, down to millitesla. So dynamically changing the behavior of the field. And I'd just like to give a short intermediate summary of what the status of the field is now, 2018, after these measurements have been done by the different groups. So this is the state in 2013. This plot shows the accuracy with which charge parity and time symmetry have been measured in a number of different systems, going from K0, K0 bar mass difference to the deuteron, anti-deuteron mass difference to the G factor of the muon and so on. And the measurements that I want to focus on are the measurements by ATRAP, ASAXA, and alpha. And I also want to point out that what is normally cited as a precision for a measurement is a relative accuracy, 1%, 1 per mil, 1 part in a trillion. But if one tries to apply this standard model extension to the measurements, one actually has an absolute scale for comparison. This is a GeV scale, which is a complementary way of looking at things. And of course, depending on which group you're involved in, you're either going to want to use in the K0, K0 or mass difference, the relative scale, because that's where you're the world leader, or in the case of the G factor or the antihydrogen experiments, the standard model extension scale, because that makes you look better. So it's not clear which is the best comparison to make, but what I want to point out are the improvements in the last years and the levels to which one approximately could go. In the case of hydrogen, antihydrogen, the most sensitive systems are the 1s-2s transition. These are the two precisions with which the value is known in hydrogen, this bar here and this bar here, and that sort of sets how far one could in principle go with antihydrogen if one had the possibility. The measurement of the hyperfine splitting in 2013 was at the percent level, so it barely shows up here, but it will show up at this level here. In 2015, the situation has already improved. The first alpha measurement of the hyperfine splitting of antihydrogen had been made, and there has been an improved measurement of the antiproton magnetic moment to a part in a million. In 2016, there are further improvements on the antiproton-proton mass difference, so that is now at the level of 1 part in 10 to the 9, and the charge difference. 2017, alpha measures the spectroscopy and improves first the hyperfine splitting by another 2 orders of magnitude, and the first measurement of the 1s-2s transition of antihydrogen is carried out to 1 part in 10 to the 10, and then in 2018, they've improved this measurement by 2 orders of magnitude. So this is where we are right now in terms of to what precision CPT has been tested. Now that CPT has been tested reasonably well, we want to look at gravity, and that will form the next part of the talk. And I want to underline, before talking about the experiments, the importance of working at very low temperatures. We're talking about atoms at 1 Kelvin moving at velocities of about 100 meters per second, which allows them to rise about 1 kilometer against gravity. If you want to do a measurement of gravity, that's not going to work. You're going to have to go to much lower temperatures, where the velocities, the initial vertical velocities, are of the order of a meter per second, or perhaps as low as 10 centimeters per second. And this means going down into the regime of temperatures of about 100 microkelvin down to 1 microkelvin. And unfortunately, the coldest antihydrogen atoms that have been produced to date have a temperature of about half a Kelvin, and that means that gravity is not going to be feasible until we find a way of cooling these atoms down to very low temperatures. However, in the case of hydrogen, the atom cannot be cooled with lasers to below about 10 millikelvin, a few millikelvin, simply because one reaches the recoil limit. The atom is very light, the energy of the transition is very high, and so one cannot cool antihydrogen to below about 3-4 millikelvin, well above the temperature range that's needed in order to be able to do a gravity measurements. So in spite of this, we're going ahead, following two different paths, either making atoms at this temperature and then trying to work with them, or figuring out how to make very much colder atoms so that we can get into this regime and actually do a real measurement. And the first group that started looking at gravity with hot atoms is, again, alpha. And if one looks at this plot in detail for much higher statistics, if you imagine that you put a plane through this cylinder, then you can count how many atoms fly upwards and how many atoms fly downwards. Of course, for a thermal source, the two numbers are going to be identical. But if the atoms start to be colder and colder and colder, at some point there's going to be a slight excess of atoms in the bottom hemisphere relative to the atoms in the top hemisphere. So this asymmetry is something that you can look at as a function of the time since the moment you open up the trap. If you wait long after the atoms have come out of the trap, you're sampling the coldest fraction and the ones where the asymmetry could be largest. And so what they have plotted here are the Z position of every single one of the atoms that they had produced. These are the red dots, and have given a upper limit to how strong gravity could be for antimatter that would still be compatible with this asymmetry, and that's the gray, the dashed line here. And what they get then is that based on their atoms, gravity for antimatter could at most be 100 times stronger than for normal matter. Okay. It's not unexpected, but it's the first measurement of gravity with antimatter. In order to actually get a real measurement, for example, the sign of the gravitational interaction, you would need to cool the atoms down to 30 millikelvin, but laser cooling could achieve that, and lengthen this magnetic shutdown period to allow the atoms more time to fall, going from the 20 milliseconds they have now to about a factor of 10 longer. And with that, they should have the statistical power then, in the coming years, to measure whether gravity for antimatter has the same sign as for matter. That's still not very satisfying. Measuring the sign is not really what you want to do. You want to do a precision measurement of antimatter's gravity, coupling to gravity. And so these two experiments, Aegis and GBAR, are trying to work on a scheme that will allow them to measure gravity more precisely. We need to start out with cold antihydrogen, and with the scheme that these two experiments are using, it's the temperature of the antiprotons that really dominates that temperature there. So if you find a way to cool antiprotons, then you might end up with cold antihydrogen as a starting point. In the case of Aegis, the idea is to mix antiprotons with positronium atoms to form antihydrogen, and if the antiprotons are cold, then the antihydrogen atoms will be cold. The positronium temperature is not really relevant compared to the temperature of the antiprotons. They should be at around a Kelvin or so. And this should lead to relatively cold antihydrogen, but at a relatively low rate. Again, we need enough rate here. The GBAR experiment is doing something different. They are bringing in the positrons in form of positronium to first form antihydrogen, but then, contrary to Aegis, they then use the antihydrogen, the formed antihydrogen, as a beam of antimatter to interact those with the remaining positronium to form a positive ion of antihydrogen. And this positive ion can then be trapped with electric fields rather than with magnetic fields in the case of neutral antihydrogen. and possibly be cooled. Again, here the rate is low, but it's worsened even more by the fact that you have two processes that are necessary for this. In the case of the Aegis experiment, this antihydrogen atom is actually not going to be trapped. We're not going to try to trap it. We're going to try to form a beam out of this atom. And in order to form a beam, we can use the interaction of this atom with an electric field gradient. Rather than trying to trap them with a Zeeman splitting, we're going to try to push them with Stark splitting. And in order to do this acceleration, we need to know when our atoms are produced. We have to make them all at the same time, which is one of the reasons for using this scheme, which allows us to actually pulse produce antihydrogen by pulsing the positron to positronium transformation and the excitation of the positronium to Rydberg positronium in order to get a sufficiently high rate. So this process is not a continuous process, as in the three-body recombination. It's a pulse process that produces all atoms at once. You can then turn on an electric field gradient and form a beam of antihydrogen atoms, which is sort of just the starting point to the real experiment. The real experiment then uses this beam and propagates it through two gratings, which will produce, by shadowing, a periodic pattern on a third plane out here. So this is the arrival point of where the antihydrogen atoms will actually impact the detector. And if gravity affects these atoms, they will slightly fall downwards, so you get a parabolic trajectory that's shifted downwards. These fringes are shifted downwards. So you can, in principle, measure the effect of gravity by measuring the fringes for different velocities. The slower the antihydrogen atoms, the less we accelerate them, the more time they have to fall, the further these fringes go down. So the atoms themselves will have to move at around 1,000 meters per second to be able to get them out and get a sufficient flux, which means that we have fall times of about milliseconds, 1 millisecond or so. So you can imagine these gratings and these detectors have to be sensitive at the micron level. This is not yet working for antihydrogen atoms, but it is working for antiprotons. And so I'll be talking a little bit in the next few minutes about the production of positronium, how we make the positronium, how we excite it in order to get antihydrogen, and a little bit about how this detection scheme can work at the precision that we want to achieve. This is a picture of the Aegis experiment. It's about 8 meters long. All this stuff here is just the infrastructure in order to manipulate the antiprotons, catch the antiprotons, cool them, get them to be placed close to the positrons, form the positrons, inject them, form the positronium, and so on. In fact, this cut-through is really just uninteresting necessary technology. The most interesting part is down here where the antihydrogen actually are formed, and that's the blow-up here on this side. So you recognize again these rings. These are the rings in which we will hold the antiprotons, or in which we hold the antiprotons. This is a small target in which positrons are injected. Positronium comes flying out, and you can see here two feeds for lasers, for infrared, for UV and for infrared, that will then excite the positronium as it rains down and forms antihydrogen in here. And this structure also allows then ejecting antihydrogen atoms out this way here, once we will have formed them. The first important step in the positronium formation is to interact the positronium with the lasers. The positronium is formed here, it spreads in all directions. Interacting them with two lasers will form Rydberg positronium, which can then interact with the antiprotons. And if you look at the produced positronium, it's orthopositronium, it has a lifetime of 142 nanoseconds. So what this plot here shows is the annihilation rate of positrons in form of positronium here at 142 nanoseconds decay time. And you see a spike at the beginning, which is positrons annihilating here in form of parapositronium, which has a much shorter lifetime. When we are on resonance for the first transition, we go from n equal 1 to n equal 3, then any positronium that would have decayed has now been excited and disappears in a way from the annihilation curve. And so we expect a decrease in the signal. This transition here is reflected by a decrease in the 142 nanosecond decay curve. And by scanning the frequency of this UV laser, one can measure the spectrum of positronium, the transition from n=1 to n=3. We use a trick similar to that of the alpha experiment, by the way, because the photons here, the positronium that is in here, is then field ionized through the second transition, the second laser. You can also then change this second laser to a longer wavelength so that the positronium that's excited is no longer field ionized, but only excited up to a highly excited state, a loosely bound state with lifetimes of microseconds, in which case, instead of decreasing the signal only, which is what you're doing in this case, you're going to decrease it at short times, but because you're populating very long-lived states, it's going to increase at long times. So to show that we've produced Rydberg positronium, we then look at the intensity of this decrease and increase as a function of the wavelength of this laser, and one can see the transition from n=3 to n=15, n=16, n=17. So we can easily produce Rydberg positronium pulsed and on command. And in principle, one can then carry out precise QED tests on positronium, and one of our plans deals with making metastable positronium, propagating it, trying to see if we can do some measurements. I'll come back to that in a minute. The other thing is to test the deflectometer, this series of gratings, and to test our detector at the same time. And to do that, we shoot antiprotons rather than antihydrogen atoms. Antiprotons are much easier to produce and to accelerate. And as they fly through these gratings, the gratings select parallel lines out of these, so that if you look on the surface of the detector, you expect certain areas in red to be where antiprotons end up. In fact, these areas in red correspond to light going through this grating, and if you shine light through these gratings, you will see these red patterns. Antiprotons might, however, be deflected. There are electric fields, magnetic fields, so that if they're pushed up or down, the annihilation point, where they end up with, is not necessarily coincident with where light ends up. And in order to have a reference, we placed one of these gratings directly onto the detector where antiprotons and light should overlap completely. So what we get is these images here. The red is what we get for light, where light shines through the apparatus. And in blue, every one of these blue dots is one antiproton annihilating. I think I can run the movie. Yes. So this is the detector that we use to see where the annihilation takes place. It's a photographic plate where when an antiproton touches the plate, it annihilates, and the resulting nuclear fragments and pions then leave traces inside the emulsion, which can then be studied under a microscope. And one can reconstruct these points to about 1 micron precision, and then look at where they are compared to where light is. So we've put all our annihilations and all our stripes from light into one single structure here. This one corresponds to that structure, and this one is the reference structure. And one can see very well that the annihilations in the reference contact plate are all coincident with light, which is what it should be. Whereas in the case of this structure here, where the antiprotons could have been affected by gravity, but more likely by electric and magnetic fields, in fact, there's a slight shift upwards in this case. And by looking at the position, the relative position for the contact plane and for this plane here, one can measure that the antiprotons are on average shifted upwards by 9 micron, which corresponds to the shift that we're looking for with antihydrogen, except that in this case, of course, it's not due to gravity, it's electric fields and magnetic fields, simply fringe fields. So what this shows is that our technique works. We have the sensitivity and the precision to measure antihydrogen interaction with gravity once we have made this beam of antihydrogen, and that's in fact what we're working on right now. The real challenges that we have to address now and in the future is that we need colder antiprotons to have colder antihydrogen, but we also need more antiprotons. Right now, at best, the alpha experiment can trap about 10 antihydrogen atoms per attempt, and we can make maybe 1 or 2 antihydrogen atoms per attempt. It's not enough. We need hundreds or thousands, so we need more antiprotons. And currently, the scheme to produce antiprotons for the experiments that are inside the antiproton decelerator is to produce them here by injecting protons onto a production target, then slowing down the 3.5 GeV antiprotons inside the antiproton decelerator, and then ejecting them at the lowest energy that the decelerator can reach, which is 100 MeV over C. At 100 MeV over C, we have a trapping efficiency of only about 1%. So this is not a very efficient way to trap antiprotons. And the real challenge is to make them slower. If we can get them to be extracted not at 100 MeV over C, but at 100 keV, then a trapping efficiency of 100% should be achievable. And in order to do that, a new small accelerator has been built and is now undergoing commissioning, which takes the antiprotons at 100 MeV over C and slows them down to 100 keV, and then distributes them via electrostatic beamlines, no longer magnetic field beamlines, to a number of experiments, which is growing. The alpha experiment is just in the process of installing a gravity module experiment. Asakusa is building a second experiment. ATRAP already has 2 experiments. And the Aegis experiment, which is currently cited here, will move to here. And a new experiment, GBAR, which is just in the process of being commissioned, has also been installed. So this ELENA ring is allowing more activities to take place at the same time. Here's a schematic of what this ring looks like. It's very small. This is about 6 meters in diameter. It dramatically increases the efficiency for trapping. And it, in fact, has another big advantage, which is that due to space charge limitations inside the accelerator, one can no longer run with a single bunch, one has to run with 4 bunches, so that when one extracts, one actually can extract 4 bunches to 4 different experiments. So you can run 4 experiments simultaneously, rather than the current scheme, which only has 1 experiment at a time. So this is a very, very good device. It was constructed in 2016 and is now undergoing commissioning. This is what it looks like. If you were to come to CERN today, you would see this device here. So that solves half of the problem. It solves the more. Now, I have to say a bit about colder antiprotons. As I mentioned before, the coldest atoms that one can achieve through laser cooling inside a trap for antihydrogen is around a few millikelvin. In fact, for hydrogen, the coldest atoms are around 8 millikelvin. That's what laser cooling allows. We need to go colder. And the 2 schemes that are being pursued by the Aegis experiment and by the GBAR experiment are to take the formed antihydrogen and then try to cool those. That's what GBAR is doing. Or to try to cool the antiprotons. So in the case of GBAR, I said before that they're trying to make antihydrogen ions, positive ions of antihydrogen, which has a very low rate. But the interest of a positive ion is that this can then be interacted with, for example, indium ions, positive ions, which can be laser cooled down to 20 microkelvin. So by having laser cooled positive matter ions, very low temperatures, one can sympathetically cool antihydrogen ions. And once these antihydrogen ions are cold enough, of the order of 10 to 100 microkelvin, then one can photodetach this extra positron with a very weak infrared line at this frequency here. And so the atom all of a sudden becomes neutral. It's hardly moving, it becomes neutral, it will drop, and by measuring the time of drop, one measures gravity. In the case of Aegis, we're trying to focus on cooling antiprotons. Antiprotons are negatively charged. So we cannot interact them with positive ions. We need to interact them with negative ions. And in fact, up to today, no negative ion has been cooled, laser cooled. The only negative ions that have a chance of being cooled are osmium minus and lanthanum minus. They're the only ones that have 2 bound states that allow laser cooling. Lanthanum minus is our best candidate, but these ions don't just have 2 states, they have 6 states. And so one needs a small army of lasers to cool on all the possible transitions. The other system we're looking into is molecular ions, C2 minus to be exact, and I'll show you the spectrum in a minute for C2 minus. In that case, we should be able to reach sub-millikelvin temperatures for the ions and then be able to cool the antiprotons to that temperature and then form correspondingly cold antihydrogen. If one can reach that kind of temperature, sub-millikelvin, then a precision on gravity measurement of about 10 to the minus 6 or better is feasible, although it's not going to be trivial. So this is the spectrum for lanthanum minus. Up to, what was this, 3 years ago, this spectrum was unknown, and so it was not possible to design a laser cooling system for lanthanum minus. Now that the spectrum has been measured by this group, they're working on trying to laser cool it. In the case of the molecule, the C2-, it's not only the scheme that allows us to cool the C2- ion by using infrared lasers. We're also going to use a new scheme for atomic cooling, which we developed. It's Sisyphus cooling, but in a magnetic field gradient, which is not something that atomic physicists normally do. But for this system here, it is very convenient to be able to populate and depopulate at different points inside a penning trap, inside these ring electrodes, in order to get down to the final limit for this atom, which is around 100 microkelvin. And we chose this system here because this is the ground state, this is the first excited state. This transition between the first excited state and the ground state, this Frank-Condon transition strength, is about 99% of the transition. So almost every single time, with a single 2.5 micron laser, we excite and we de-excite. With 100 cycles, the atom is almost never lost. And so we have very, very high efficiency. If we wanted to be 100% efficient, we could use a second laser, which is a that's this transition here, a 4.5 micron laser. This setup is undergoing tests. We've built the source for C2-. We're now in the process of trapping C2- and of testing that we can actually excite this state here. We've got the right laser. Now it's just a question of spending a bit of time on it and showing that cooling can work. So in the last few minutes of this presentation, I'd like to focus on a few other systems that people are thinking about, which are antihydrogen-like, but which open up further areas of investigation that are currently not being pursued. I already mentioned charge neutrality for antihydrogen atoms. This can be driven much further than the part in a billion measurement that's been done by the alpha experiment up to now. One should be able to go by several orders of magnitude further by carrying out a dedicated measurement rather than a parasitic measurement. In the case of positronium, this system here currently decays with a lifetime of about 142 nanoseconds, but we're working on a scheme to extend its lifetime to microseconds or perhaps even milliseconds, and to form a beam of positronium, which then allows thinking about carrying out the same scheme that we have for antihydrogen with positronium, and to test gravity with a purely leptonic system. So you eliminate any baryonic coupling, potential baryonic coupling, and you see only lepton sensitivity. And in fact, you can even think about doing this with muonium. A muon, a system made of a mu plus and a mu minus, or of a mu plus and an electron. The same methods that we're working on here also carry over to muonium. And then one has a second generation test, either in a purely leptonic system, or if this muon couples to the antiproton, one forms muonic antihydrogen, gravity on a second generation antihydrogen atom. Another thing that is very interesting to think about is that this muon, because it's so much heavier than the electron, is very close to the proton, or the antiproton in this case. And you may be aware that the antiproton charge radius is being probed extremely precisely in muonic hydrogen. There's a discrepancy between the proton charge radius measured by muonic atoms and the radius you get when you scatter electrons on the proton. And so this would be a way to also test the antiproton charge radius at the same time when doing spectroscopy of this system here. You can also try to form atoms made of a proton and an antiproton, protonium, or of an antiproton and a deuteron. Now you have a purely baryonic system, no leptons anymore. And again, you can think of carrying out a gravity test with that, but also of carrying out spectroscopy. And in particular, the deeper bound states of antiproton-proton atoms are sensitive to the strong interaction. And this might be a way of spectroscopically measuring the strong interaction at relatively large distances, a bit like muonic hydrogen is being used right now. The ions of antihydrogen are being used by GBAR for gravity, but one can also use them to test CPT. In fact, this ion is not the best one. The best ion is this one, where you have a molecular ion of hydrogen or of antihydrogen. And in this particular case, the proton to electron mass ratio, mu, is being measured to 1 part in 10 to the 15. So this ion, if we can make it, and there are some ideas how to get there, should allow doing a much more precise measurement of charge to mass ratio than we can currently do with the antiprotons and positrons individually. And finally, there's an experiment that is working right now that is being prepared called PUMA, which is trapping antiprotons and building the trap in such a way that they can be carried over a few hundred meters to another accelerator at CERN, ISOLDE, and combined with radioisotopes to form antiprotonic atoms, but with short-lived isotopes. And just like one can measure the radius of the proton with muonic hydrogen, one can measure the radius of these nuclei with the antiproton. But the interesting thing about this is that these radioisotopes, these short-lived radioisotopes, generally have a neutron atmosphere around the nucleus. And that is what the antiprotons will annihilate on first. So what one really measures with this kind of atom is the shape and the radial distribution of the radioisotopes, of short-lived radioisotopes. They cannot be brought to the antiprotons, but the antiprotons can be brought to them. I will skip this next slide. I'll just flash it for information. This is a scheme to measure gravity with positronium. To come to the scheme that we're thinking about to measure gravity with protonium, I already talked about it a little bit, that there's the interest of measuring QCD-induced shifts and broadenings relative to the QED atomic spectrum. This protonium system has already been produced. You inject antiprotons into hydrogen, you automatically get protonium. But because there's such a strong mixing of the protonium that is formed with the hydrogen, one gets very rapid annihilation, and so it's impossible to actually study the system the way it's currently being made. One can only measure the spectroscopy by fluorescence detection, and that is then limited in precision by the detector resolution. So this is not a very good way, but we've thought about an alternative way which could be feasible, and that is to combine inside the same apparatus antiprotons and H- ions. H- is a well-established ion of hydrogen. The binding energy of the electron is about 0.20 electron volts. And if one has these two interacting with each other, and one photoionizes the hydrogen ion, one ends up with hydrogen. The hydrogen can immediately interact with the antiprotons to form protonium, and because this is happening in vacuum at a very low density, this protonium here will not quench, it will not stark mix, and it will not annihilate rapidly. So one can actually start thinking about studying it with lasers to induce transition between this state and other states, or between deeply bound states or annihilating states. So the spectroscopy is already possible, and there's even a nice little trick that one can play. If this hydrogen is not in the ground state, but actually in an excited state, then this cross-section here increases by many orders of magnitude. So we should be able to form a lot of cold Rydberg protonium, which can then either be formed into a beam, or perhaps even trapped. If it's long-lived enough, several milliseconds or so, then one could in principle even trap it, and maybe even cool it even further. So this would then allow carrying out gravity measurements in precision spectroscopy. So to conclude, the advances in the last few years on spectroscopy with antihydrogen, antiprotonic helium, as well as precision measurements with antiprotons, are now at the level of 1 part in 10 to the 12. And these experiments have the potential to reach even further precision in the coming years. Several orders of magnitude are feasible. And the first tests of the weak equivalence principle are becoming feasible. It's not going to be this year, it's not going to be in the next 2 years, because CERN is shutting down all accelerators until 2021, but it will happen in the period between 2021 and 2024. There will be first gravity measurements in that time, with initial precisions of the order of 1% or per mil. Furthermore, work that we're carrying out to get to this is also leading to being able to perhaps reach even higher precisions and ultimately be able to form atomic fountains and use laser interferometric techniques to go beyond the few percent and per mil level down to parts in a million or even better. And then I mentioned these exotic anti-hydrogen-like systems, which will require a lot of patience and ingenuity to make and to control, but these open up the door to additional new kinds of tests of gravity in purely baryonic or leptonic systems, but also high sensitivity measurements of properties of antiprotons, of positrons, and thus of CPT. So this field has been accelerating in the last few years and is continuing to accelerate for the next decade or so, with an impact on many different areas of physics. And with that, I thank you for your attention.
Bueno, pues muchas gracias. Gracias, profesor Teucer. ¿Alguno de ustedes tiene preguntas respecto a esta? Un momento.
Hi, we can achieve Bose-Einstein condensation with antimatter.
Sorry,
We can achieve Bose-Einstein condensation with antimatter. Is possible with...
So to reach, to be able to form a Bose-Einstein condensate of antihydrogen, we need to go down to temperatures of microkelvin or below. This is also the goal for the gravity measurement. So the temperature range should be feasible in the next years. I don't want to put a number down right now, but maybe by 2030 we should be able to have the temperature range, but also solve the other problem, which is a question of the amount of antihydrogen atoms at that temperature. Right now, to go below the laser cooling limit that we have for antihydrogen, the idea is to do evaporative cooling. And evaporative cooling wastes most of the atoms. If we have to do evaporative cooling, then we may end up with 1 or 2 antihydrogen atoms at microkelvin temperatures. So that's the wrong way to go. And however, it's the only method that's been proposed up to now. We need to find a way to go, without using evaporative cooling, to below the recoil limit. And there are some ideas that are very, very speculative for now. We have to go through the calculations to see if they're feasible or not. But if we can develop that technique to go below the recoil limit, then we can have the numbers and the temperature. And so Bose-Einstein condensate could be feasible at around 2030. I made that prediction in 2010, that 20 years in the future we will have Bose-Einstein condensate. So we have to do it by the time of my retirement.
Yeah. So when you use the microwaves to count the population of the atoms, how can you be sure there won't be a problem with like annihilating all of them?
So the power that you can put into the microwave that you inject into this apparatus is very low, and the likelihood for a transition for a microwave spin flip is correspondingly low. So it takes on average 20-30 seconds of exposure to the microwave field to flip half of the atoms. This is what the alpha experiment has calculated, and it's also what they measure. If you could have a higher intensity microwave field, then you would flip the atoms more rapidly, but it doesn't really matter. You want to flip them. You want to see how many atoms have been lost through the microwave flip, because it's only on resonance that this loss can happen. And that's what you're trying to measure. Are you on resonance or not? And if the atoms are all lost within a microsecond, it doesn't matter, as long as you know that it's because the microwave is on resonance.
Hello. I thought I understood when you said that you were measuring gravitational interaction. I imagine it's the Earth's field.
Yes.
And would there be any advantage in perhaps considering a stronger field? I mean, obviously in the Earth it's not possible, but perhaps near the Sun or with measurements at stars or something to get a better.
You would get a much nicer signal, that's for sure. The experimental challenges are a little bit daunting to go somewhere else. I think we're not going to be limited by the gravitational field itself for as long as we're not going beyond 10 to the minus 6, 10 to the minus 8 precisions. If we want to go beyond that, then it might be beneficial to have a stronger field, but then probably we should have invented other techniques that will also allow us to go beyond what we have. The interferometric techniques that are being thought about now for these systems have already been developed, and gravity tests at the level of 10 to the minus 12, 10 to the minus 13 with normal matter systems are already feasible. So the real challenges will not really be the gravity, the strength of the gravitational field. It's rather going to be the statistics. We're going to end up having not enough atoms or not cold enough atoms. And I think that's going to be easier to address than to get a strong gravitational field.
¿Otra pregunta?
Hello. When you say that the tests of weak equivalence principle are becoming feasible, what kind of precision do you really respect with other modern weak equivalence principle tests, such as torsion balance test or another space tests?
So the most precise gravitational tests are on atomic systems, with atomic fountains or atomic fountain-like systems where you use interferometric techniques. That's where you get 10 to the minus 12, 10 to the minus 13. The torsion balance is always going to be limited by the systematic effects that you have. So as long as we're using the same techniques as the atomic gravitometers, we will not hit a brick wall. I'm very optimistic that we will solve the other problems at some point. And so we really can rely on the advances made with manipulating atomic systems, trapped atoms, ultra-cold atoms that are slowly accelerated upwards in form of a fountain and are then probed interferometrically. That technique is what we want to use in the long-term future. So this, yeah.
So this technique could lead to an upper bound of the ELENA parameter?
Yeah. Yeah, so I'm not optimistic that we will see a difference. I'm rather convinced that we will see exactly the same interaction. And so in the end, we'll have an upper bound on any possible difference between matter and antimatter.
Okay, thank you.
One last question? Someone else? Bueno, pues entonces damos por terminado este coloquio de investigación. Muchas gracias. Gracias. ¡Ay, aquí hay una pregunta! ¿Sí? Bueno, one last question.
Yeah, fine.
Hi. Are there some current ideas on how to drive experiments about antimatter interaction with biological systems?
With what systems?
Biological systems.
Ah, okay. So I didn't talk about it at all because it's not particle physics, but we have done some experiments with interacting antiprotons with living cells, actually, to investigate the possibility of doing tumor therapy. And we saw that this is indeed a very efficient way of doing it, much more efficient than with protons, but also much more costly. So we're not pursuing this any further. We understand more or less now the physics and partly the biology. There is room for further experiments, for example, trying to see whether, what we did was using healthy hamster cells. You'd like to see that this works also for cancer cells, ideally human cancer cells, and ideally in vivo, not in vitro. So there is still room for further experiments, but CERN isn't pushing for this, nor is the community of radio-oncologists. They're not really pursuing this idea very much. There is, however, another theoretical chemical question that is starting to be investigated in the context of tumor therapy, but also in other contexts, and that is to see what happens actually at the molecular level when an antiproton interacts with a molecule. Is it possible to engineer a molecule in such a way that the antiproton is attracted to one or another of the components of the molecule by tailoring the shape of the molecule? So that's been done. There's some theoretical chemists working on that and exploring this. And you can go a little bit further than that, and this may be the last thing I want to mention, which is really a crazy idea. If you can engineer that kind of interaction by forming a molecule, is it possible to build a molecule in such a way that you get a sort of symmetric interaction that would actually allow encapsulating antiprotons? Building a molecular trap for antiprotons. And we're looking into that right now. So if we get funding, we'll have a student work on the chemical calculations.
Thanks.
Bueno, pues ahora sí, muchas gracias. Gracias a todos por venir. Gracias.